Okay, let's take a look at these practice problems for chapter 5. What's the relationship between the two compounds that we see here? Well, you see that they both have the same molecular formula. Both are C4H10O, but they have a different connectivity, don't they? So could anybody tell me what would be the best answer here? A, B, C, or D? Exactly. Thanks, Sean. Constitutional isomers, right? Um, different connectivity. Good. Let's move to the next one. Is this alkene a cis trans or neither alkene? Well, what's not shown here in the bond line structure are the two hydrogens that are on opposite sides. So how would we describe this one? Exactly. This would be a trans compound. Yeah, exactly. You could call this an E compound too, but this is a trans compound. Okay, shown here is Crestor, a medication used to reduce cholesterol. Is the highlighted alkene cis trans or neither? Well, it would be helpful to draw in the hydrogen. Thanks, Sarah. Perfect. Draw in the two hydrogens, and we can clearly see that this is a trans alkene, right? Because the two hydrogens are identical. They're on opposite faces of the molecule. And there we have it. The next one's kind of a tough question to do remotely. It just says locate the chirality center. So remember, a chirality center is when we have a carbon, so carbon attached to 4 different groups. Okay, so 4 different groups. All right, so let's see if we can locate a chirality center. I'm going to highlight a carbon. Could anybody tell me this one in yellow that I have highlighted in yellow? The one in yellow highlighted in yellow, is that a chirality center? Yes or no? Definitely not, right? Because it's got 2 methyl groups on it, right? So this wouldn't be, this isn't, this isn't, this isn't. None of those things are chirality centers. Also, the sp2 hybridized carbons, those aren't chirality centers. Neither is that because they're only attached to 3 groups, right? You have to be attached to 4 groups in order to be a chirality center. Well, this is an sp2 hybridized carbon, so it doesn't leave us with much. This is a CH3. That can't be attached to 4 different things. And so our only chiral carbons in the molecule are going to be this one, and this one. Those would be our stereocenters. Each one of those carbons is attached to 4 different groups. So there we have it. The next question, I think, is in the exact same vein. Okay, looking for chirality centers. Right, this cannot be a chirality center because it's a CH2 group. Right, it's got 2 hydrogens on it. Therefore, it is not a chirality center. But if you look at this carbon, you can see it's attached to 4 different groups, isn't it? It's got an oxygen, it's got this group, it's got a proton that's not drawn in, and it's got all of this, you know? So it's definitely got 4 different groups attached to it. And you can use that same rationale to determine that you have chirality centers not only at that carbon, but you also have one here, 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 and here. And so we have 4 chiral centers in this molecule. All right, sorry, 5 chiral centers, my mistake. 5 chiral centers in number 5. All right, what would be the relationship between these 2 compounds here? Would these compounds be enantiomers, identical, or neither? And I'm on question number 6. Somebody says identical. Any other answers? Okay, well, let's see here. Are they identical? Well, we've got a couple of options here. I mean, you could just think about um, you know, rotating this molecule. If you were to rotate it this way around an axis like this, if you rotated it 180 degrees, you would end up with this, right? So you'd end up with something that's identical. So the answer is identical. Another way to do that is just to determine that if the IUPAC name is the same, right? But the only thing, Katana, is that we haven't covered alcohol nomenclature. So you could just look at the compound to determine whether it's R or S. And you can see that both of these stereocenters, this is R and this is R, therefore they must be identical. to each other. We could just get a little bit of practice on that. So if I draw this compound, why is this an R compound? Well, if I draw the proton going back, this is number 1, this is number 4, this is number 2, and this is number 3. So we go 1, 2, 3. It's going clockwise, and therefore it is an R compound. Okay, what's the relationship between these two guys? Anybody? Yeah, absolutely. They're non-superimposable mirror images, aren't they? Right? We just flip the dash to a wedge, or the wedge to a dash. And if you check the stereochemistry of these two, this is an R compound and this is an S compound. And so that's another way you could do it. The next question, question 8, is kind of a funny question. It just says draw the enantiomer of the following compound. So all we're required to do here is to redraw the carbon skeleton and flip every wedge to a dash. So we had wedge here, here, and here. And then flip every dash to a wedge. So do one here, and I'll put one here. And there you go, my friends. I've drawn the enantiomer. Not much to that one. The next one is R or S. There's only one chiral center in the molecule. It's right here. We have a hydrogen going in the back. So we'll pencil that in. The hydroxyl, the oxygen is 1. The hydrogen is 4. If we look at this carbon, it's attached to oxygen, hydrogen, hydrogen. This carbon is attached to oxygen, hydrogen, hydrogen. So we don't have a tiebreaker. So we have to keep going from there. And once we keep going from there, then we get to an oxygen that's attached to a hydrogen here. And then up on the top, we have an oxygen attached to a carbon. Well, the oxygen attached to a carbon is going to take higher priority, right? Carbon is a higher priority than a hydrogen. So we just keep going. And so this would be group number 2, and this is group number 3. And so we go from 1 to 2 to 3, which is counterclockwise. And so this is an S compound. So this stereochemical configuration here is S. Same kind of question here. I'm going to redraw this compound. So if I redraw it like this, we actually did one like this earlier today. It's almost identical. If we put in the proton, so the oxygen is going to be 1, the hydrogen is going to be 2. This is going to be 3, and this is going to be, sorry, why do I keep doing that? The hydrogen is going to be number 4. This is going to be number 2, and this will be number 3, right? The reason why is this carbon is attached to carbon, carbon, hydrogen, and this one is attached to carbon, hydrogen, hydrogen. So that's my tiebreaker. So I go from 1 to 2 to 3, which is counterclockwise. So that would be S, but the hydrogen is coming out in front. And so we reverse it, and this is an R compound. All right, we have Crestor again, and it says assign the configurations of the 2 chiral centers as being R or S. So there's this one here that I have highlighted in yellow, and then there's this one I have highlighted in green here. Let's see if we can do the one in yellow first. So we'll draw the hydrogen, which is coming out in front. So the oxygen will be 1, the hydrogen will be 4. This carbon is attached to carbon, hydrogen, hydrogen. This carbon is attached to carbon, carbon, hydrogen. This is my tiebreaker. So this would be group number 2. This is group number 3. I have 1, 2, 3. It's going clockwise, which would be R, but I reverse it because the hydrogen is coming out towards me, and so that's an S carbon. So let me just delete all this spinach here. Just write on here that this is S. And then for the neighboring chiral center, what am I doing here? There we go. We're going to draw the hydrogen coming out like this. This is going to be number 4. This will be number 1. This carbon is attached to carbon, hydrogen, hydrogen. This carbon is attached to carbon, hydrogen, hydrogen. So no differentiation. We keep going. This carbon is attached to oxygen, oxygen, oxygen. This carbon is attached to oxygen, carbon, hydrogen. And so my tiebreaker is here. And so this would be group number 2. This would be group number 3. So I go 1, 2, 3. So I'm going counterclockwise. I reverse it, and I end up with an R stereocenter. So this stereocenter would be, oops, that's not right. The stereocenter here would be R. All right, so the one on the left is S, the one on the right is R. Okay, now we've got Plavix. Worked for the company that developed Plavix years and years ago. And it says assign the stereochemistry of the chiral center in here. Got our proton here. So let's see, the nitrogen is going to be number 1, the hydrogen is going to be number 4. This carbon is attached to oxygen, oxygen, oxygen. This carbon is attached to carbon, carbon, carbon. So this is our tiebreaker. This is going to be number 2. This will be number 3. So we go 1, 2, 3, which is clockwise, which would be R, but the hydrogen is coming out in front. And so we reverse it, and this compound would be an S compound. Number 13, which of the following is the correct structure for S2-pentanol? Well, we didn't do alcohol nomenclature, so I'll just kind of, do this one with you. But if you have a pentanol, so if you have 2-pentanol, you'd have a 5-carbon chain, and then it means that the alcohol would be on carbon 2. So you'd have 1, 2, son of a gun, 1, 2, 3, 4, 5. So it's got to be either C or D. And so, or sorry, B or C. And so if we look at B, we would go from 1 to 2 to 3, like that, which would be S. And if we do this one, we go 1 to 2 to 3, which would be, looks like it would be S, but we would reverse it. And so C would be an R compound. And so the answer must be C. All right, what's the correct IUPAC name for the following structure? So this is just a little bit of nomenclature for us. So let's see here. If we want to number this compound correctly, we're going to have to go something like this. So 1, 2, 3, 4, 5, 6. So we've got a 3-ethyl. So it's a 3-ethyl, 2-methyl, hexane. Oh, jeepers, they're all 3-ethyl. No, sorry, the last two are wrong. So it's got to be either A or B. And so we have to determine whether the stereocenter is R or S. So let's delete all this. There we go. We'll put our hydrogen coming out in front. So let's see, this is going to be our lowest priority group. Our highest priority group is going to be the isopropyl group because it's branched. All right, this carbon is attached to carbon, carbon, hydrogen, whereas this one is attached to carbon, hydrogen, hydrogen. So there's our tiebreaker. So this is 1, this is 2, this is 3. So we're going to go 1, 2, 3, which is counterclockwise, and the hydrogen's coming out in front. So we reverse it from S to R. And so the compound is B. It is R, 3-ethyl, 2-methyl hexane. So this is an R compound. What's the correct name for the following IUPAC structure? So first of all, we're going to count the carbons in our longest carbon chain. 1, 2, 3, 4, 5, 6, 7. So it's a 3-methyl heptane. So that means it's either B or D. We just need to determine whether it's R or S. This one should be pretty quick because our lowest priority group is going back in the page. So the highest priority group is going to be the longest chain. 2 would be the second. This would be the third, and then the hydrogen is the fourth. We're going 1, 2, 3, which is clockwise. So this is an R compound, and so the compound must be 3 or R, 3-methyl heptane. What's the relationship between these two structures? Can anybody answer 16 for me? What's the relationship between these two compounds? Yeah, they're diastereomers, aren't they? They have the same configuration at one stereocenter and opposite at the other, right? So this compound is actually R, and this one is S, R. And so they're diastereomers, absolutely. Yeah. The next one, what about the next one? I'd say with this one's the same thing, right? They're diastereomers, aren't they? Right? They're non-superimposable mirror. They're stereoisomers, but they're not non-superimposable mirror. They're stereoisomers, but they're not mirror images. Sheesh, I'll get it eventually. All right, so these would be diastereomers. Here it says draw a diastereomer of the compound. Kind of a goofy question, but we could do it. So if we were to draw something like this, where we have this hydroxyl coming up, and if we switch this one to up, or we could do this, where we have this hydroxyl group going down, and this one going down like this. Keep in mind, those are not identical compounds, right? They are not the same compound because you have this carbonyl over here. So they're definitely not the same compound. Oh, shoot. Draw all the stereoisomers of this compound. Well, they're all shown up here. They're all shown, or actually, sorry, most of them are shown up top. So let me take these two, copy, paste these two. Come on, paste them over here. And then, of course, you would also have, so we'll say this, this, and then we've got two more, don't we? So we've got this guy, which is drawn up there. This is up, this is down, and then we have, it's an enantiomer where this is down and this is up. So those are all the possible stereoisomers of this compound. Again, keep in mind that these two are not meso. So not meso. There's no plane of symmetry in there because of the carbonyl. Okay, the next one. Which of the following is the diastereomer of this compound here? So we're looking for something that's a diastereomer. This one's a little bit tricky. You kind of have to look through them all and do some rotation here. It can't be C because C doesn't have a second chlorine, right? C only has one chlorine, right? So it's got to have two chlorines in the molecule. And so it might be this one, or this one. So we can eliminate C. So we'll eliminate C. And so then what are we going to do? Let me see here. I'm just looking at it very carefully. I guess we could either rotate everything or we could assign stereochemistry to every stereocenter. Seems kind of long, but we could do it. This is S and this one is S. And then if we do this one is R and this one is R. So those would be enantiomers. Then if we look at this one is S and this one is R. And so this one would actually be the diastereomer, would be this guy here. And if we look at the last one, this is the identical compound. This is S and this is S. So the answer would be B for that one. All right. If you want to do it by bond rotation, you can. I'm not going to go over all that right now. I've taught it enough to know that students who are really good at bond rotation are really good at it. And students who are not so good at it usually get it wrong. So be very careful if you're trying to do bond rotation with this one. I mean, you could kind of do what Sean said before, where if you look at these two compounds here, okay, you can see the first stereocenter is identical, but in the second one, they just swapped the methyl and the chlorine. So you could say, well, they're diastereomers based off of that, and that would work too. Okay, either way works. In fact, that might even be easier. Anyhow, this one here, I'm going to skip number 21 because I even wrote here in my notes, I would not ask this on a quiz. You have 4 stereocenters in here. So you have 2 to the power of, where is it? 2 to the power of 4, which equals 16. I'm going to leave this as an FYI. I would never ask this, okay? That's way too complicated because there's too many different meso compounds that you can get. So I actually need to remove this from this problem set. The next one, you can see that some of the stereocenters are the same, and some of them are different. And so this would just be a pair of diastereomers, right? You can see that this one is the same, and that's the only one that's the same. All the other ones are different, right? This one's different. These two are different. So they must be diastereomers based off of that. The next one, there's not a lot of room here, so I'm going to redraw the compound. It says designate this Bishop projection as being R or S. So we'll put our hydrogen here and our ethyl group here. Remember, if it just ends like this, that means it's a methyl group, right? So I'll just put Me here like this. So number 1 is going to be the oxygen. Number 4 is going to be the hydrogen. Methyl and ethyl are just carbon-based chains. And I told you that the longer the chain is, the higher priority it has. And so this would be 2. This would be 3. So we go 1, 2, 3 like that, which is clockwise. So that would be but we reverse it to S because the hydrogen, remember, is coming out like this. So this is an S compound. The next one, assign each stereocenter in this guy. Well, the one on the bottom, this is not a stereocenter. So not a stereocenter, because it's got two hydrogens. But the one on top is a stereocenter. So let's just kind of re-scribble it down here and see what we can get. So we've got a bromine here, a hydrogen here, and on the bottom we've got two hydrogens. All right, so let's see here. Actually, that's not a stereocenter either, is it? Now that I look at it, not a stereocenter, I always tell you guys how much I hate trick questions. What the hell, man? There's no stereocenter in this compound, right? Because if you take CH2, CH3, this is an ethyl group. So that's a dumb question. All right, let's move on. Number 25, identify the relationship between these two structures. Why don't we take the Newman projection and draw a bond line structure of it? Or we could, try to draw a Newman projection of the bond line structure. I don't know. We could do either one, really. Would work. Why don't we do a Newman projection? Students are usually really good at these. So let's see. If we were to draw this, there's our carbon in the back. There's our carbon in the front. So we've got a methyl group going straight up. We've got our chlorine. Is the chlorine, this chlorine here that I have in the black circle, is that going to be going to the right or the left in the bottom? Exactly. Thanks, Kiana. It's going to be going to the right, isn't it? Absolutely. So I'll put my chlorine over here and put my hydrogen over here. Then in the back, I have my cyclopropyl down at the bottom, like that. And then at the top, I have two groups over here. So which way is the hydroxyl going to be pointing? Well, it's on the same side as the chlorine. So we'll put hydroxyl here, and then we'll put a proton over here. So if I compare, this structure with this Newman projection over here, I mean, what's the difference between them? Well, one of the carbons is identical and the other one's flipped, right? You flip the hydrogen and the hydroxyl. So therefore, they must be diastereomers of each other. And that's it. If you wanted to try to assign the stereochemistry, you can do that, but it's not really required to solve the problem. Is there more? Yep, there's a couple more problems here. What's the relationship between these two compounds in 26? Could anybody answer this one? Get trans 2-butene. So this is trans, and this is cis 2-butene. What would be the relationship between these guys? Exactly. They're stereoisomers. Yeah, more specifically, they're diastereomers. Good. 27, is the following alkene cis trans or neither? Well, I've got two fluorines. Could anybody answer this one? Two fluorines on the same carbon. So it's neither. So remember, whenever you have two groups that are identical on the same carbon, it can't be cis and it can't be trans. It's impossible. It has to be neither, right? Because I mean, what would the fluorine isn't cis to anything and it's not trans to anything, right? Neither fluorine is cis or trans. Cis and trans, you got to have identical groups. All right, the last one is draw R4 ethyl octane. This is how I would do it. I would start by drawing the parent. So I'd say 1, 2, 3, 4, 5, 6, 7, 8. Then on the fourth carbon, I'd put an ethyl group. So 1, 2, 3, 4, like this. And what I always do is I draw is a dash. And then if I have to shade it into a wedge, then I shade it in after. So let's take a look here. We've got a hydrogen coming out in front like this. So this is going to be our lowest priority group. This will be 1, this will be 2, this will be 3. So we go like this, which is clockwise. That's R. We reverse it, so it would be S. So this means I drew the wrong compound. And so all I have to do is take this guy and shade this. I need a different colored pen. And convert that into a wedge. And there you go. R4 ethyl octane.